The space of continuous maps between two differentiable manifolds is a metric space whose induced topology is the weak topology. But in general, the space of continuous maps with a strong topology is not metricable. So an interesting question arises to understand whether there exists another structure in that space that could be useful for applications. We will see that this is indeed the case, and that the space of continuous maps between differentiable manifolds is a Baire space for the strong topology. Let us define the strong topology in the space of continuous maps between two topological spaces X and Y. Indeed, we are going to define a base of this topology. And for that, we consider a continuous map F from X to Y and an open set W of the Cartesian product of X and Y that contains the graph of F. And we define N of F and W as the set consisting of the continuous maps from X to Y such that the graph of G is contained in W. The sets of this form are actually a base of a topology, and we are going to call this topology the strong topology of the space of continuous maps. Indeed, what we have is that this W is essentially telling us how much G can deviate from F. And because of this, when we consider X and Y as manifolds, we obtain again the strong topology in the space of continuous maps between two manifolds. Indeed, in order to convince ourselves of this, consider the strong topology in the set of continuous maps between the line and itself. Here, we can consider a continuous map from the line to the positive real numbers. And in this case, there is a base of the strong topology such that the sets in the base are the following form, are of the form N of F epsilon, okay, where this set is just the set of continuous maps from the line to itself, such that the modulus of fx minus gx is smaller than epsilon x for every x. And again, this in this way, we have that the maps in this set are the continuous maps G, such that at the point X, they deviate from fx less than epsilon x. So yeah, this topology, when for instance x is equal to r and y is equal to r, has to be again the strong topology. And this is the definition of the strong topology for the more general case in which we are considering topological spaces and not just manifolds. Okay? Indeed, when we are dealing with manifolds, we can give an analogous description of the base of the strong topology as for the case of the space of maps between Euclidean spaces. Okay? If M and N are manifolds, then we can consider that N is a complete metric space, and so we consider a complete metric D in N, and we can define for every epsilon, which is a continuous map from M to the positive real numbers, and every continuous map from M to N, we define N F epsilon, which is just the set of continuous maps such that the distance from fx to gx is less than epsilon x for every x, here for every x in M, okay? And in that way, we obtain, again, a base of open sets for the strong topology, okay? The issue is that if we fixed one continuous map F, there is no accountable basis of neighborhoods of F if M is not compact and the dimension of N is greater or equal than 1. Of course, if M is compact, since the weak topology is metrizable, okay, then and the strong topology is the same as the weak topology when M is compact, then the strong topology is also metrizable, and this space of continuous maps with the strong topology is first countable. Every element has a countable basis of neighborhoods, a countable neighborhood system, right? So if N is compact, yes, we can provide a metric for this space. If the dimension of N is equal to 0, then there are very, very few continuous maps from M to N. For instance, if N is just a point, then there is just one. And of course, a space with one point is metrizable. So yes, we have a complete metric, a trivial complete metric. But the issue is that if we get out of these trivial examples and M is not compact and the dimension is greater or equal than 1, then fixed map, there is no countable neighborhood system. And so this space does not have a topology induced by a metric, okay? Indeed, we are going to see in the exercises this kind of property, the lack of a countable neighborhood system. But in particular, this implies that this space does not have as good properties as the same space with the weak topology. Yeah, because it's not metrizable. Okay, so what can we do with this space? Because it's not a metric space, but is it possible to consider another structure that is going to be useful for the applications? And the answer is yes, because this space, it is indeed a Baire space. What is it, a Baire space? If we have a topological space, we say that X is Baire if any countable intersections of dense open sets is dense. It is not necessarily open, okay, but it is dense. An example of a Baire space is a complete metric space. This is always a Baire space, okay? So in particular, every second countable Hausdorff manifold is a Baire space, okay? We want to show that if M and N are manifolds, then the space of continuous maps between M and N is a Baire space for the strong topology, right? And we are going to show a more general result. We are going to see that any weakly closed subset of the set of continuous maps is indeed a Baire space in the strong topology, okay? Let us explain the hypothesis, okay, that is here in the statement of the theorem. A weakly closed subset is by definition just a closed subset for the weak topology. So we are going to consider D is going to be a complete metric in N. Okay, we can do this. And we are going to define the following sets. If epsilon is a continuous map from M to the positive real numbers, we know that the set n of f epsilon is just the set of continuous maps such that the distance from fx to gx is smaller than epsilon x for every x. But we are going to define an m bar of f epsilon, which is going to be essentially the same definition, but we allow that the distance is between fx and gx is smaller or equal than epsilon x for every x. Okay, so the first one is contained in the second one. Right. What do we need to prove? First of all, we are going to consider Q is a weakly closed subset, right? And now we are going to consider U and is an open subset of Q. Okay. Consider now A0, A1, A2, and so on, a sequence of dense open sets of actually Q, right? And what we want to prove is that is the following. We want to show that the intersection of U with all the AI is indeed non-empty, because that's what you need in order to show that this set over here is dense. What you have to prove is that the intersection with any open set is with any arbitrary open set is non-empty. So if we consider a sequence of dense open sets and another open subset of Q, then this intersection has to be non-empty. That's our goal. Okay, let's go. The first thing is that A0 is dense by hypothesis. It's a dense open set. So the intersection with U is actually non-empty. Here we are using that A0 is dense. And in particular, is a non-empty open set. So there is an element F0 that belongs to the intersection of A0 and U. Okay, so we have U that is an open subset of Q and a sequence of open dense subsets of Q. Okay, and F0 that belongs to A0 intersection U, right? What we get is that there exists, because of the definition of a neighborhood system for the strong topology, there exists a continuous map from n to the positive real numbers such that Q intersection with this m bar of F0 epsilon 0 is contained in A0 intersection U, right? Because this is an open subset of Q, right? And indeed, we can suppose, by considering epsilon not small enough, that it's always smaller than 1, right? So this is our first map, F0. Now we can consider the intersection of A1 with n f epsilon 0, which is going to be still, since A1 is an open subset of Q, this is going to be an open subset of Q still, right? So in this case, we are going to find, since A1 is dense, right? This intersection over here is non-empty because it's the intersection of an open subset of an open dense subset of Q with this map whose intersection with Q is an open subset of Q and non-empty open subset of Q, and because of that this intersection is non-empty. And again, we can consider F1 as an element of this intersection, and by choosing some epsilon 1 we get that we can find F1 and epsilon 1 such that this property happens. We just have to choose F1 as an element of the intersection, and then the existence of epsilon 1 is a consequence of the definition of the base of the strong topology. And here we can suppose, for instance, that epsilon 1 is smaller than epsilon 0 divided by 2. Okay? So we keep playing this game, and what we get is that we can choose a sequence of maps. All these maps are indeed contained in Q, okay, because in particular F1 is in A1, which is contained in Q, and F2 and F3 and so on. And we get that this, by doing this choice, this iterative choice of the maps Fn, we can get to obtain that this intersection is contained in An intersection with n of Fn epsilon n, and we can get also that epsilon n plus 1 is smaller than epsilon n divided by 2, and so on. All right? This is what we have. Okay, what are we going to do with this? Okay, so let's write over here what we get. Okay, and what happens here, right, is that Fn plus 1 is contained in n of Fn epsilon n. And so this implies that the distance between Fn x, Fn plus 1x is smaller than epsilon n, right? But epsilon 0 is smaller than 1, epsilon 1 is smaller than epsilon 0 divided by 2, and so on. So this is going to be smaller than 1 over 2 to the power n for every x in M, right? This implies that if we fixed a point x in M, then the sequence of the values of x by the fn's, this sequence is indeed a Cauchy sequence. And so, since D is a complete metric in N, what we get is that there exists the limit of fnx when n tends to infinity, right? But obviously, what we're going to get from this property over here is that, okay, the distance between Fn x and Fx is smaller or equal than 1 divided by 2 to the power n for every x in M. And in particular, that's going to imply that Fn converges to F uniformly on compact sets. So Fn converges to F uniformly on compact sets. Very good. But we know that all Fn's belong to Q, okay? Because every Fn, for instance, here, which is containing this set that is a subset of Q. Every Fn is an element of Q. So we have that Fn belongs to Q for every n. Very good. But since Q is weak closed, and the topology, the weak topology, is a topology of a uniform convergence on compact sets, that implies in particular that Fn converges to F in the weak topology. And since Q is weakly closed, then we get that F belongs to Q. So we get F that belongs to Q. Okay? We want to see that it also belongs to U and all the AIs. Okay. So let's remind ourselves of we have Q intersection with M bar. Okay, is contained in AN intersection with N of Fn epsilon N. I think it's that, yeah. So the first one is that Q intersection M bar of F0 epsilon 0 is contained in A0 intersection U. Very good. So what we get is actually that the M bar of okay, this space over here, intersection Q, is contained in N of Fn epsilon N. But if we get N of M bar of Fn plus 2, epsilon n plus 2, intersection Q is contained in N of Fn plus 1, epsilon n plus 1, intersection Q, which is going to be contained in N of Fn epsilon n because of this property. Okay, so what we get is that M bar of Fn epsilon m intersection Q is contained in N of Fn epsilon n for every m greater or equal than n, right? Good. That's what we want. Very good. And now, what we have is that all the, this implies that in particular, Fm belongs to this m bar of epsilon n, of fn epsilon n, for every m greater or equal than n. In particular, its limit satisfies the same property, and its limit is f. So we deduce that f belongs to m bar of fn epsilon n for every n greater or equal than 0. Okay? Nice. Let's see what we can do with this. Right. The first thing, of course, is that f belongs to that set and also belongs to Q. Okay, we already proved that. And if we get the definition, that is contained, sorry, here I'm seeing a problem, should be F0, that is going to be contained if here we have n plus 1, the intersection of Q and m bar of fn plus 1 epsilon n plus 1 is contained in an intersection with n of fn epsilon n. Okay, so it's contained here in epsilon n minus 1 intersection, right, for every n greater or equal than 1. So, but this implies in particular that f belongs to the intersection of all the AIs. And it also belongs to Q. And it just remains to show that it belongs to U. But very good, because f, we are in a very good spot because f belongs to m bar of f0 epsilon 0, okay, which is contained by definition, by construction, in a 0 intersection U. So f also belongs to U. And we get that this intersection over here is indeed non-empty, right? Okay, so we get that the intersection of these sets over here is still, all the sets are dense open sets, all the AI, and the intersection is still dense. It's still an a dense subset of Q. We saw that the space of continuous maps between differentiable manifolds is a metric space whose induced topology is a weak topology. And moreover, that such space of continuous maps with a strong topology is a Baire space. In order to study the properties of the space of CR maps, we are going to introduce jet spaces in the next lecture. And by using that technique, we are going to be able of seeing that indeed the space of CR maps is metrizable for the weak topology and is a Baire space for the strong topology. Thank you for your attention.